There's a lot that can be learned about a quantum mechanical system by inspecting the wave function. So here's one to start with. We have all of the trappings of a wave function here. We have an amplitude, psi sub 0. We have a special function, exponential. There are two terms in the exponential. There's this minus I omega t, which looks a lot like sinusoidal time dependence. That comes right out of the time-dependent Schrodinger equation, and that's the best interpretation of what t being time is, and omega then being angular frequency. The first term is more unique. You have an x squared in there and these constants. I think we can make sense of what it all is. Let's do it by looking at dimensions. H bar has dimensions of angular momentum. So if x is position, which it is, if omega is angular frequency or angular velocity, m times omega times x squared has dimensions of angular momentum provided m is mass. So from that we can deduce that m must be a mass, and it even says m is the mass in the statement of what this is. So the question is, show that this is a harmonic oscillator. That's what we have. We have a wave function, and show that this is the wave function for a harmonic oscillator by finding the potential energy that would give rise to this wave function. We can do this by putting this wave function into the Schrodinger equation and finding what potential energy would make this solve the Schrodinger equation. We start out with what's usually the first equation in any quantum mechanics textbook, with I h bar d psi by dt on the right side instead of just E psi, which would be the time-independent Schrodinger equation. Let's go ahead and insert this wave function into this equation, take the derivatives, and solve for V. V is the potential energy. Went ahead and evaluated the first of the two derivatives in x. No derivative in the second term. In the right side of the equation, I went ahead and evaluated the time derivative. Evaluate this position derivative one more time, and then you can cancel those exponentials because there's a factor of the exponential in each term. I'm going to do that all in one step. I'm going to take this derivative again, and then I'm going to cancel the exponentials, and there I have what's left. Simplify it further and solve for V. Now you have you have four terms altogether. If you look closely, you'll see that two of these terms are constants that can add together, and then you have the x squared. So simplify it one more step. We have a constant plus a term in x squared. Now just a little reminder that constants added to potential energy are meaningless and can be neglected, and so we throw away that 1/2 h bar omega term, or leave it in if you want to. It won't make a difference. So I'll just say that the potential energy is 1/2 m omega squared x squared. Now it has this form, 1/2 times something times x squared, which definitely looks like a harmonic oscillator. And in fact, the harmonic oscillator in quantum mechanics has this potential energy. You might remember it more as 1/2 kx squared. Angular frequency omega is the square root of elastic constant over mass, which it is. Replace that omega with root k over m, where k is some elastic constant, and you have exactly 1/2 kx squared, which is perfectly quadratic, and it's a harmonic oscillator. Any potential energy that's quadratic is a harmonic oscillator. So that's what we have here with this wave function expression. Keep a close hand note of that expression that were given in the problem statement. That is, in fact, the ground state of a quantum mechanical harmonic oscillator. You know oscillators are localized. If I have a pendulum over there, it's not over here. So as it oscillates, it's very well defined where it's oscillating about. The point is that a harmonic oscillator is a localized wave function, so it's normalizable. Let's normalize it so we can solve for the amplitude psi 0. And the motivation for doing that is I would like to take that wave function and calculate the uncertainty in position x and the uncertainty in momentum p, and see if it's consistent with the Heisenberg uncertainty principle. But I can't get those if psi sub 0 is all I have for an amplitude, because when I solve for the uncertainties in x and p, I'll have psi sub 0 in it, and I won't know what to do with that. So let's find what that amplitude is. So, you set the integral of psi star is the complex conjugate, so the complex conjugate of the wave function times the wave function integrated over all space, set it equal to 1, and solve for that amplitude. So the e to the I omega t cancels out because you do a complex conjugate, and so those are gone. And so all you have to do is integrate e to the minus m omega over h bar x squared over all space. Well, how do you do that integral? It's not the simplest thing to work out. We find a lot of special integrals in quantum mechanics, and you'll accumulate a little library of them. This is a special integral that comes from a collection of functions called gamma functions. You could just say, look it up in a table of definite integrals, but it's a lot better to understand the origin of the special functions. Let's look at this integral of minus infinity to infinity of e to the minus x squared dx, which, yes, you would look up and find is the square root of pi. And you may use that. You have to do a little u sub in order to make the m omega over h bar x squared rectify with the differential dx, but that's not too challenging. Let's talk about where this integral comes from. And for that, we need to pay a little visit to Wikipedia and ask about gamma functions. So the gamma function is written in terms of this general form integral, where you have the variable t, and you've got a power of t, and you have e to the minus t over tau to the beta. That's the most general form for a gamma function. That integral equals the gamma function of, we'll say of, this n over this beta times this tau raised to the power of this n divided by this beta. Now you look at the integral we want to solve. We want to solve the integral from minus infinity to plus infinity of e to the minus x squared dx. First problem is that this is an integral from 0 to infinity, not minus infinity to infinity. That's easily dealt with by recognizing that e to the minus x squared is an even function. So whatever that integral equals from 0 to infinity, it equals exactly half of what it is from minus infinity to infinity. So it's okay. You can just put a minus infinity sign there and then put a little 1/2 in front, and everything will be the same. This integral we want to solve can be likened to the gamma function by saying that tau equals 1, beta equals 2, and n equals 1, because there's no x in front, so it's x to the 1 minus 1. Which means what we want to find is the gamma function of 1 over 2, 1/2. We're going to look that up. Gamma function of 1/2 times 1 to the 1 over 2. But that 1/2 is going to be ignored because we actually want the integral from minus infinity to infinity, not 0 to infinity. So we turn to a table of gamma functions then and find gamma of 1/2. Gamma of 1/2 equals square root of pi. So the integral from minus infinity to plus infinity of e to the minus x squared dx is the square root of pi. Yeah, so the table of gamma functions is something that I think is really, really useful in quantum mechanics. So let's use that to calculate the normalization. We now have an expression that we can use for this exponential inside of an integral. So I'm going to go ahead and use it. I did a u sub without explicitly saying what it is. So you have to work that out on your own, but that's 1 equals psi squared, and then the integral, it comes out to root pi, and this root h bar over m omega is the consequence of the u sub, where I had to turn dx into d root m omega over h bar x. Solve this for the amplitude, psi 0, and you notice you've got something to the 1/4. This is a very, very well-known expression because it's the normalization that goes in front of the ground state of the quantum mechanical harmonic oscillator. So put a box around that and be prepared to use it a lot. So let's go ahead and write out the wave function, though, then using that normalization. So I have the psi 0 in front, and then e to the minus all the stuff that's given. I want to simplify this notation a little bit too. So, and this is a very common practice with harmonic oscillators. to rewrite this m omega over h bar times x squared as something called xi squared. So we're going to use a variable substitution. Xi equals x times the square root of m omega over h bar, so that you don't have to keep writing it all the time. It's going to be very helpful when it comes to quickly gauging what integrals are equal to, especially using the gamma functions. So this is the form we're going to use. The last one here. We'll let the exponential contain minus xi squared over 2 minus I omega t, where xi is just a conglomeration of the constants times x. So let's find the uncertainty. First, the uncertainty in x, and then the uncertainty in p. So the uncertainty of an observable, like position or momentum, is the standard deviation of that observable within the wave function. So we can find the variance and take the square root to have the standard deviation. Standard deviation is the square root of the expectation value of the observable squared minus the expectation value squared of the observable. We need to find each of those quantities. Let's start with the expectation value of x. I'll set up the calculation. It's the integral of complex conjugate of the wave function times the operator, x. X is technically an operator, even though it doesn't do anything to the wave function, times the wave function, dx. Now we do have this thing where we have two different variables at play here. We have xi and x, and so I'm going to favor xi over x because it makes the exponentials much cleaner. So replace x with x equals root h bar over m omega xi. That means replace dx with root h bar over m omega d xi. The limits on the integral don't change at all. Infinity is still infinity. I'm not going to solve this integral. I'm not going to even bother. Don't look it up. Just guess. You should be able to look at that integral and know immediately what it equals. How do you know what it equals? Are you all saying the same thing? That's an odd function being integrated from minus something to plus the same thing. That's always 0. So that it's an odd function, meaning that if you change the sign of xi, you get an equal and opposite value for the integrand. So from the lower limit to the upper limit, the area under that curve adds up to 0. So the integral is 0. Whenever you take an integral of an odd function from minus something to plus the same thing, you get 0. Let's look at the expectation value of x squared. Again, it's integral of the complex conjugate of the wave function times the operator times the wave function. In this case, the operator is x squared. I went ahead and just did away with the e to the I omega t business because the complex conjugate destroys that. And since x, is technically an operator, but we know it doesn't do anything to anything. It doesn't change anything. So I just went ahead and wrote the wave function squared. And so we have to solve this integral. And again, you have x and xi in the same integral. You need to choose one. I favor xi. So when I turn this x squared dx into xi squared dxi, I pick up a factor of h bar over m omega to the 3/2. And now I have this integral. I could use integration by parts to take that integral down to the gamma of 1/2 function that we've already seen. And in fact, I've seen that done repeatedly in textbooks just to, I guess, illustrate how integration by parts works in case people forgot. But we've already employed the table of gamma functions to solve integral of e to the minus xi squared dxi. Why is it any less legitimate to go back and use the same table of gamma functions to evaluate xi squared e to the minus xi squared dxi? So there's the general expression for the gamma function equals that integral. And in this case, n now is 3 because you have xi squared, so you have the variable to the 3 minus 1, which is 2. Beta is still 2, and tau is still 1. We want to find the gamma function of 3 over 2, gamma function of 3/2. Go to the table of gamma functions, and you find gamma function of 3/2 is root pi over 2. So this integral equals root pi over 2. Technically, the integral from 0 to infinity equals root pi over 2 times 1 over beta, which is 1/2. So when you turn that into an integral from minus infinity to infinity, the beta, which happens to be equal to 2, can be thrown out. So make sure you follow that reasoning. And you can replace this integral with root pi over 2. I'll replace the psi squared with the amplitude we just normalized for. Square root of m omega over pi h bar is psi 0 squared. You have this term to 3/2 still, and we have the gamma function of 3/2. And replace that gamma of 3/2 with root pi over 2. And simplify, and we find that the expectation value of x squared is h bar over 2m omega. So if we want to find the standard deviation of x, take this and subtract the expectation value squared of x, which we determined already is 0. I'm left with the square root of h bar over 2m omega. Now let's work on momentum. And again, we need to find the standard deviation of momentum. First, we'll find the expectation value of the momentum operator, and then we'll find the expectation value of the momentum operator squared. Remember, the momentum operator is minus IH bar d by dx. Start with the expectation value of p. So I have the integral of the complex conjugate of the wave function times the operator times the wave function. Momentum operator is minus IH bar d by dx. If I want to favor xi as my variable, I need to turn d by dx into d by d xi. This is how you do it. Xi is root m omega over h bar times x, so d xi by dx is root m omega over h bar. Bring the d xi over to the other side, and you have 1 over dx is root m omega over h bar times 1 over d xi, which we'll just claim to be d by dx and d by d xi. And so we replace d by dx with that. Root m omega over h bar times d by d xi. And that's the momentum operator. So you have to evaluate that derivative, so go ahead and do that. But before we do that, let's see if you can intuitively say, what should this be? So you have a mass on a spring. It's going up and down, up and down. It spends as much time going up as it spends going down. What's the average value of momentum? Let's see if we get that here. I'll bring all the constant stuff out front, and I'm left with the integral of, okay, I got to take one more derivative. So take one more derivative, and you have integral of minus I e to the minus I squared. And again, that's an odd function. So when you integrate an odd function, you get 0. Expectation value of momentum is 0. What about the expectation value of momentum squared? So you have the complex conjugate of the wave function times the operator times the wave function dx. So the operator now is momentum squared. So it's I h bar d by dx squared. And that's my d by dx again, is that. And again, the e to the I omega t and e to the minus omega t cancel. And this is just the psi sub 0 that we saw for squared out front. Let's take our derivative twice. That's a little bit of work. We need to do it. And also you do I squared, you get a minus sign out front. I'll simplify it. I guess we'll first of all bring constants out, get the integrand cleaned up, and now I begin my differentiation. So I evaluate that derivative twice. I went ahead and did it, didn't ask anybody's permission. There are a couple lines of algebra between these two, but when you do that derivative, you end up with this. So pause the video if you need to, and perform the integral to convince yourself that this is the function that we are integrating. I look at that integral and I recognize the two integrals that are in front of me because we've already dealt with both of them. The first one is the gamma of 3/2 function, and the second one is the gamma of 1/2 function. So I just have to pull those up. So gamma of 3/2 was square root of pi over 2, gamma of 1/2 was square root of pi. So just put those in there. Simplify everything down, and you realize you've got this simple function. M omega h bar over 2 is the expectation value of momentum squared. So if I want to know the standard deviation of momentum, it's the square root of this minus 0. And so that's the uncertainty of momentum, the standard deviation, literally, of momentum when your wave function is the ground state wave function of a simple harmonic oscillator. Put this together with the sigma sub x, the uncertainty in x, and solve. So the uncertainty in x was root h bar over 2 m omega. Let's combine that with this, h bar m omega over 2. And sigma x, sigma p, the uncertainty in x, the uncertainty in p, oftentimes in textbooks, that's delta x, delta p, is h bar over 2. Now you might ask yourself, well, shouldn't it be greater than or equal to h bar over 2? Why is that equality? It's actually equality. There are certain quantum mechanical states that reach the equality in the Heisenberg uncertainty principle. They're called minimum uncertainty wave packets. Basically, if the state has this quadratic dependence in it, if it's a Gaussian, or if it's a ground state of a harmonic oscillator, you end up having the minimum uncertainty case where you have equality instead of greater than or equal to. There is a general condition that's worked out in our textbook for when you have minimum uncertainty that we'll deal with when we get to chapter 3. So what we've done here is we've taken a mystery wave function, determined that it describes a harmonic oscillator, that was cool, normalized it, found the standard deviation of the position observable, found the standard deviation of the momentum observable, multiplied them together, and found that their product is both consistent with the Heisenberg uncertainty principle and a special case of equality in the Heisenberg uncertainty principle. That won't normally be true. We will normally have something greater than h bar over 2. So that gets us going with the uncertainty principle. And we're going to come back to it, and we'll introduce the generalized uncertainty principle later, which allows us then to come up with uncertainty principles for other observables.